All right, so I did 9.3 and 9.5 kind of together because they're very connected, and I'll do that for this as well. So 9.3 is on logarithms and logarithmic functions, and 9.5 is common logs, natural logs, and change of base. So logarithms are the inverse of an exponential. So here's the exponential we talked about back in 9.1 with some arbitrary base a. It's a little bit small and faint, but some arbitrary base a. Anything to the 0 power is 1. So you always have 0, 1, and then anything to the first power is itself. So 1a, whatever a is, whatever the base is, will be there. And of course, this is when the base is positive, that it goes upward. If the n greater than 1, if it was less than 1, then you would have a decay function. The reflection over line y equals x, the inverse, of course, would be switching the x and y. So you'd have that point, 1, 0, and this point at a1, a comma 1. When you switch the x and y for an exponential, you're, instead of having some base to the x equaling your y, the base to your y will equal x. That's the inverse. The x and y have been switched. But how do we then solve for y? Well, you might think, oh, I could take the y-th root, but you don't know what the y-th root is. So you can't really isolate the y. It would still be the y-th root. It would still be the index value. It wouldn't be isolated. You can't just divide by b, because then it would be b to the y minus 1, but not y by itself. So we're kind of stuck with our knowledge of how to isolate the y at this point. So here is the introduction to a whole new system of numbers, a system of representing stuff called logarithms. And so the logarithm, shorthand, we say log, base b, it's the same base when it's in exponential form or in log form. These are just two formats of saying the exact same thing. So this is the little subscript. It's lower and smaller, the base, and the idea is that you're trying to solve for your exponent. And so that is why it's equal to that. And then your argument is what the exponential would have been equal to. So the easiest way to think about it is this counterclockwise motion. B to the y is x. You can see the equal sign, but you have to skip over. B to the y is x. If you have a note card available to you, I would highly recommend that you write this down on it, because it's going to be the key to a lot of the properties as well as the solving of logarithmic equations. If you don't have a note card, then I suggest you memorize it. And hopefully by doing a lot of practice, it'll become kind of second nature to you anyways. So here again, the inverse of this, we briefly talked about how the x and y have changed, and to get y by itself, you write it as a log. We talked about the vocabulary in passing, but here it is written down, the base. This is called the argument, and then this would be equaling your exponent. The bases have to be equal. And so this same phrase and the same value. So the lesson also talked about common logs, and the common log is when you have a log of base 10, because we are in the base 10 number system. So we kind of assume that when there's nothing here, that it's base 10. Okay, so we talked about how, if you have an invisible coefficient, that means 1. If you have an invisible exponent, if you have a base, the invisible exponent is 1. If you're missing something, then it's a 0. When you have a square root, the missing index is a 2. Now we have this missing base is an invisible 10. So it's all about the context and what is kind of the most common scenario, because then it's shorthand, leaving it off because it's the common thing. So base 10, the natural logarithm is coming from a lot of things that happen in nature, and that involves this letter, which represents a number, E, about 2.7. We'll talk about E a little bit more in a moment. So the natural log, ln, the natural log, is the same as a logarithm of base E. If you look at your calculator, you'll notice that there's a log button right by a exponential, and there's an ln button where the that shares a button with the E, typically. Not always, depends on your calculator, but they're normally sharing a button or right next to each other, and I'll talk more about the calculator later. One other thing to note is that when we talked about exponentials, you could never end up getting a negative for your range. Your fraction just got smaller and smaller and smaller and smaller and smaller and smaller and smaller. A half, then a quarter, then an eighth, then a 16th, etc. if your base was 2. And since you're getting smaller fractions here, if you do the inverse, you're going to get smaller and smaller fractions here. Again, never crossing this y-axis. That is called a vertical asymptote. When you never cross something, it's an asymptote. When it approaches, it's an asymptote. You can actually cross a horizontal asymptote, but not in these cases, and you'll learn more about that in calculus. So a vertical asymptote you can never cross, it just gets closer and closer and closer to it. And so that is getting closer and closer to the line x equals 0, the y axis. X equals 0 is the equation of that line. And because of that, your domain for the logarithm is always 0 exclusive, so parenthesis, and then it keeps going to the right, so infinity. So you can change forms from a logarithm to an exponential by following that pattern of base to the exponent equals the argument. So 3 squared equals 9. Invisible 10 to the m is x. W to the r is k. 8 to the 0 is 1. 5 to the negative 3 is 1 over 125. And invisible e to the 7th is 1096.63 approximately. So anything to the 0 is 1. Anything to a negative power will be a fraction. And then e, we're going to locate, hopefully be able to locate on our calculator. You can also go from an exponential to a log. I do this by setting up log, putting my base, putting some blanks, and then filling them in as I go through it. So 2 to the 4th is 16. 3 to the negative 2 is 1/9. 7 to the 1st is 7. 7 to the 1st is 7. M to W is K. M to the W is K. 10 to the 3rd is 1,000. Now because this base 10, there's a shortcut. You can just say log and not have the base because it is the common log. E to the 3rd, so E to the 3rd is 20.0855 approximately. Now instead of saying log base E, we can just write ln. Again, the shortcut for that natural log when the base is E. Now your calculator is great with log base 10 and the natural log, the log base E. Depending on how fancy your calculator is, you might be able to do other bases pretty easily. The TI-89, for example, has the ability to do a log in any base. The shortcut is diamond 7, and the syntax then is you put your argument, comma, your base. So if I wanted to enter something like this problem right here, log base 7 of 7 is 1. Again, log base 7 of 7 is 1. You must take a log of something, and it does not mean times. It means that that's what you're evaluating it at. That's your input. So in this case, you would say log 7, comma 7. That's not so differentiable. Let me find a better one. Here, it would be log 1/9 in parentheses, since it's a fraction, comma 3, and then close your parenthesis when entering it in the 89. You can convert those so that you can use any calculator, scientific or the 84 or the 83, but primarily those scientific can do it very nicely when it's in base 10. So the way you do that is you do log of your argument divided by log of your base. So it's like you go across the top here and then you go across the bottom. So log base x over log base a. When you do that, don't forget to end your parenthesis so that you're really doing log of the x divided by log of the a rather than accidentally saying log of x times log a. Log x divided by log a as instead of log of x divided by log of a. So I put it here as well with different letters just to reiterate. It's log of the argument divided by log of the base. It's kind of nice when the base is b and the argument, oh, look at that, it's a, and then a comes before b. Hey, I just figured out a new trick, the a before the b, a on top of the b. So log of 9 divided by log 3, and we should know that 3 squared is 9, so you could evaluate this even without change of base because it's probably something you're familiar with. 3 to what power is 9? 3 squared is 9. But using your calculator, you can now type in log 9 and parentheses divide by log 3, and you should get 2. 8 to what power is 12? Well, 8 to the first would be 8. 8 squared would be 64. So 12 is definitely closer to 8 to the first, 8, than it is to the 64. So we should be much closer to 1, and when we use our calculator, we can approximate it. In this case, it's a good idea to go to 4 decimal places. It's kind of the normal convention is like 3 or 4 places because even 1 decimal place will create pretty substantial rounding error, especially if you have a larger base when you're working with it. So we try to only round at the very end of our answer, and we try to go out at least 3 places, but typically 4 is requested. Again, 5 to what power is 1? Well, anything to the 0 power is 1, but you can also do log 1 divided by log 5, and you'll get 0. Here, log 42 divided by log 3, 3.4022 when rounded to the nearest 4 places. So here it's asking you to evaluate this, and you can type this literally in your calculator because you have a log base 10 function on a scientific or graphing calculator. The 89s, it's a little bit more disguised. You probably would just use that diamonds 7 feature and say base 10. But in any case, 3 times log 10. You can also figure out what log 10 is, that it's 1, and evaluate it that way if it so happens to be something that's easy to calculate. Log 100 divided by log 7. Log 100, that's 2 divided by log 7. I'd have to figure that out, or I can again just do change of base with my calculator and do this whole calculation. ln of 5, so you should have an ln button on your calculator. Even those 89s, the 84s, the 83s, the scientific, there should be an ln button. ln, put in 5, hit enter, round to the nearest 4 places. There should also be an e button somewhere. E, and then normally it puts in a little caret already for you, and you just hit 5. If not, you can hit the caret button yourself and hit 5 and then enter. So we're going to practice more on solving in the 9.6 lesson, but you already can kind of handle these with the information I've already given you. 5 to the third is x. Well, 5 to the third is 125, so 125 equals x. Using change of base, we get that 4, this would be 4. You can think to yourself, 2 to what power is 16 and get 4 as well. And then here, x squared equals 36. Well, we already know how to handle getting rid of a square. You just take the square root. Now, when you take a square root, you normally have a plus or minus. However, the minus is extraneous. You cannot have a negative base. It's just one of our conditions. You also can't have a negative argument. So you can have a negative exponent, but no other negatives. So again, arguments must be positive. So this x right here, the argument must be positive, meaning it must be greater than 0. So that is the domain. It has to be greater than 0. Here's the y-axis, here's the x. You can see that it's only from greater than 0. It doesn't even include 0 because it's an asymptote. And here, kind of like the HK from before, this is the log just shifted to the left 3 units. It's got a different base, a base of 5, but the same general exponential shape being inversed, so it goes like this. If I've moved it over 3 units to the left, your domain will now be that it has to be greater than -3. Or again, you can just say, well, this argument has to be greater than 0, so the x would have to be greater than -3. When you're talking about domain, you're looking for the x values. So I hope that that helped a little bit. The scientific calculators, graphing calculators, if you need to look up where to find these buttons, just Google away, or feel free to message me and I can show you.